My name is Dan Combest and I work for ENGYS, and today I'm going to be talking about an extended multi-physics framework for modeling heterogeneous transport and reaction kinetics. So throughout my talk today, I'll start by talking about multi-physics in general, then I'll go into some of the development work that we've been doing here at ENGYS with something we call the Unified Solver framework, talk about verification cases, talk about some necessary physics that was needed to be added to the USF to accomplish our actual heterogeneous catalysis application, and then finally leave you with some take-home messages. So multi-physics, it's kind of the grand challenge of CFD. Everyone wants to do that, I think, when they first start with CFD, and it's very complex, to say the least. So multi-physics, we could define it as systems that involve transport phenomena through multiple fluid and or solid domains. So that's heat, mass, momentum. Then there's also this idea of exchange phenomena at an interface between these domains. So mass transfer limitations, energy transfer limitations. And there's very familiar application areas: electronics cooling, electric motors, when we couple that with even more complicated equations, heat pipes, there's phase change, and then heterogeneous catalytic processes. We typically, even though we want to model everything, we typically have to simplify based on design priorities and resources, computational resources, human resources, capability resources of our software, things like that. So when we do this simplification and we're using OpenFOAM, and there's typically, there's greater than 100 different discrete solvers. This isn't counting foam extend. There's a lot of code duplication. And for new users, there's this discoverability and ease of use kind of hurdle that needs to be overcome in the very beginning. There's 4 different pressure definitions. There's 2 different flux definitions. There's 2 distinct material property frameworks. There's the thermophysical properties, there's the transport properties, and then there's additional submodels for specific solvers. And if we're talking more about multi-physics and multi-region, there's pretty poor multi-region coupling performance with CHT multi-region foam, solely, mostly due to the explicit region coupling of that solver. At ENGYS, we've worked to develop what we're calling the Unified Solver framework. It's a modular framework in which solver building blocks, we've got momentum, we've got energy, radiation. These different building blocks can be combined and coupled together arbitrarily, of course within the constraints of the algorithm. And the solver algorithm has dependencies between each one of these modules, and it's not necessarily a linear program like something that we'd see in the application solvers folder inside of standard OpenFOAM. We prioritize implicit coupling. So when it's possible, the implicit coupling is done between regions. Overall, the end goal is simplicity and maintainability of the code base and extensibility. So being able to extend this to fluid structure interactions, or maybe a specific application to joule heating, and then also provide flexibility for its actual use, because it's very difficult to design something in the very beginning that's so general and be able to apply to many, many different types of applications. So just talking about a simple CHT verification case, inside the USF, CHT was the first application area as this development goal. And this particular test case was 1 fluid, 5 solids. There's coil heating sources around this particular device. In the end, we were able to get identical results versus the partitioned approach that's used in CHT multi-region simple foam. Here's just a simple animation comparing a region coupled on the right and a partitioned on the left. There's significant speed up and convergence. In this case, we see speed up, and in other cases, we've seen up to 100 times speed up. So this is very problem dependent. If we did all solids instead of a fluid and several solids, we'd see the USF Solver converge in one iteration. All right, some of the necessary machinery that needs to be added in order to actually perform our heterogeneous catalysis application is species transport solvers. And in this case, we're working with a gas, and the formulation of this gas phase transport is based loosely on row reacting buoyant foam. So if you're familiar with that solver, we're able to capture species transport based on mass fraction, and this specific solver transport module in the gas couples the heat of reaction in the gas phase to the energy equation in another module, the CHT module that I just mentioned. For the solids, however, we needed to add something new, which was a solver to capture the species reaction diffusion physics inside of the solid itself. And so something that's, I would say, a little unique is that the porosity of the solid is captured. We have the mass fraction of each one of the species, but then we also have the tortuosity of the solid structure itself. So coupled with the porosity and tortuosity, we're actually able to capture some of the complex structure of the porous media itself, more so than we would with another model. Also, we have a reaction rate over here. So we're able to capture the contribution of the heat of reaction within the solid that's heating up the solid and also heating up the species diffusing inside of that. And then most importantly, because we're prioritizing implicit coupling, the coupled wall boundary condition for species diffusion between the fluid and solid, if we have multiple solids touching each other, then that's something that is already within this framework. And we can also include things like mass transfer resistance at the surface. We can have heat transfer resistance at the surface, things like that, and use one-dimensional models to kind of represent things like a deposition on the surface of a catalyst particle. In terms of a straightforward verification, this was a simple case of mass fraction at each one of these walls, north, south, east, and west. And we're modeling a reaction diffusion example for this simple reaction. In the end, what we're comparing is the mole fraction and the temperature across the centerline cuts from west to east and north to south. And if we're looking at the north to south line, we can see these solid lines right here. This is out of helix. And if we see these hash marks, the plus marks, X's, stars, boxes, these are the values out of star, another commercial code. So for mole fraction, we see identical behavior. It's 1-to-1. For temperature, we see nearly 1-to-1. We see a slight over prediction in helix just at this one point right here. But if we look at the scale, so this is a meter by a meter, we're off by a fraction of a degree here in this one point. However, if we look in west to east line, we see complete agreement in both the mole fraction comparison and then also in the temperature comparison, comparing these two software. So I would say this is a fairly good verification against an industry trusted software. So now let's get to heterogeneous catalysis. This is something that is near and dear to me. And I'll talk about that in a little bit. So heterogeneous catalysis, it's a very huge body of study within science and engineering. And today I just really want to talk about packed beds. So packed beds can be chemically reactive systems with species transport, natural and forced convection. There's composition changes because of the species transport. There's conduction. There's diffusion. There can be radiation if it's really hot. There's generation and consumption of mass and energy. There can also be interaction with catalytic species inside of the solid. And as I mentioned before, there can be contact resistance at domain interfaces. Now, with all of those modeling challenges, this is actually a simulation through complex multiple regions of solids and fluids. So now we have another challenge that involves accurately capturing this system and capturing all the geometry and capturing and meshing everything properly. So if this looks familiar, this is actually work, so related to work that was done in the 6th OpenFOAM workshop many moons ago by myself. And I think back then I was answering basic questions still being answered. So I really did a lot of work on the momentum transport. A lot of it was proof of concept. How do we mesh? What's the mesh composition? What do the layers need to look like? How many layers do we need? What's sufficient? What turbulence models should be used? And at that time, OpenFOAM technology was really still developing. It was a lot different than it is today. GGI was new. Cyclic BC was moving aside because GGI was being created. This was even before AMI. And implicit region coupling was something that was new. And I believe it was even presented at this workshop by Ivor Clifford. And he had some nuclear engineering application at the time. In my previous work around 2009, the near-miss model was used, adding something like 2% of the space of a particle, so 2% of the diameter of the particle spacing in between. And the reason why this was done is because a commercial meshing approach was used with Gambit, if you have ever used that tool. It's very challenging to use. It's completely different than a cut cell approach that people might be familiar with other commercial codes. But Gambit, I used that to generate tetrahedra, and then those were converted to arbitrary polyhedra. In general, the mesh was very poor quality. The size of these cases was less than 10 million cells. It was a very trial and error approach due to the nature of the meshing tool, and just the sequence and workflow was very arduous to get through this entire sequence of things, and it took months and months and months and months to actually get good results. So from there, a lot's happened. And the specific case that I'm talking about today is a packed tube of Raschig rings. Here's just some parameters about the packed bed itself: 3 centimeters, and a radius of the Raschig ring is 0.5 centimeter. Tube diameter is 20 centimeters. The bed height, so this is greater than 1 meter, but for the sake of not going through a lot of HPC resources, I did about half of this bed, and an arbitrarily chosen tortuosity of 10 and a porosity of 0.3. So these are realistic, but it's a very complex structure inside of this porous media. So we expect to see some interesting results. Within this, we're doing a reaction within the solids only. And here, this is just a simple exothermic reaction of H2 and CO2 making CH4 and 2H2O. And in reality, it would be much nicer to do a water gas shift, to do an equilibrium reaction where there's an exothermic and an endothermic reaction. But for this case today, I'm just going to focus on the exothermic reaction. A particle Reynolds number of around 2000 was chosen. Why 2000? Well, if you look through the literature and you've seen experimental results, you know that a particle Reynolds number around 1000 is around the transition Reynolds number from a laminar to turbulent flow, maybe a little bit less. So here we're just making sure that we're in a turbulent regime when we're using our solver. Within this current approach, instead of using the near-miss model, now we can model particle contact. And this was meshed with helix hex mesh. Overall, we're able to generate much higher quality meshes, and this is simply because helix hex mesh and this cut cell approach, it's a quality-driven approach in that it meshes with the idea that it generates high-quality cells that will run well with these types of solvers. This case several meshes were generated, but one I'll talk about today. Typically, they're between 80 and 120 million cells, and they're hex dominant, they're multi-regen. And for this case, around the inlet and outlet, they're about 10 millimeters. Near the tube wall and particles, we're talking about 1.2 to 0.6 millimeters. For the tube wall, we have 100% layer coverage. For the particles, we have about 88% layer coverage. And the first cell height on the tube wall and the particle are very small, so they're fractions of a millimeter. In terms of boundary conditions, we have the velocity that matches the Reynolds number, we have a fixed temperature inlet, and then we have a composition of CO2 and H2 that are coming in. These are all fixed values. For the outlet, we're using an inlet-outlet boundary condition, and the reason why is because in case there's circulation at the outlet to stabilize the solution. Otherwise, we can just lengthen the entire domain and then use a general outlet boundary condition. For the tube wall itself, it's no slip, it's fixed pressure, it's adiabatic, there's zero flux. I mentioned that if we wanted to use the water-gas shift and have an equilibrium reaction, if we wanted to remove some of the reactants through, say, a membrane at the wall to push a reaction one way or another, that would also be a great example of how the solver could work. For the particles, it's no slip for velocity, fixed flux pressure, and then all of the temperature and mass transfer, mass transport, it's all implicitly coupled at this boundary. Just a little note, we're fully capable of adding mass and heat transfer resistance through a 1D model if we wanted to. For this case, I did not. We're using a compressible solver, so we're using JANF thermo. There's perfect gas assumption, Sutherland transport. It's a steady state RANS simulation. So we're using simple K omega SST, second order bounded schemes. Because we're using a steady state solution, we're under relaxing a little bit. And in terms of the overall workflow, so meshing was performed. So the meshing was set up inside of the Helix GUI, and execution of Helix hex mesh generated an 80 million cell mesh. On 560 cores, this took about 5 hours, and this speaks to the complexity of this domain because most of that time was spent in snapping and layer addition. And one thing that I can say is that there was actually a deviation from the default settings that we recommend, and the deviation was adding more snapping and smoothing iterations at the interface because I wanted to make sure that, one, I resolved all the particle surfaces very well, and number two, I had nice surfaces that conformed to the starting geometry so that when I added layers, I had nice layers on the surface. So if we had actually reduced the snapping iterations, it might have been adequate for a simulation and might have significantly dropped this time right here. Case setup was done in Helix GUI and then run in a separate utility called case setup. And then finally, solving was performed using Helix solve. Overall, the entire bed at this Reynolds number, we have less than a Y plus of 10. And 10,000 iterations took around 22 hours on 560 cores. So that's 12,000 core hours about. In terms of the output, there's several things that we like to look at. And on the macro level, we like to look at things like pressure drop and reaction conversion and heat balance. Pressure drop because that tells an engineer how much the pumping cost might be through this reactor. But we're more concerned about the interstitial information about each one of these principal variables that are being used and being computed inside of the solver. So in terms of results for the interstitial flow, we can immediately notice thermal gradients. We see in the very beginning the entrance of the reactor, we see very hot, and then we see it start to slow down or at least start to cool off a little bit. So towards the outlet, it's a little cooler. We see almost a very uniform temperature profile in the very beginning, and we also see some temperature gradients inside of each one of these particles themselves. We see conversion of methane from the entrance of this reactor, so we see very low methane mass fraction, and then at the very end we see methane being produced at the outlet, so that's That's great. One thing we do see is dispersion behavior. So we see deviation from plug flow. Classically, I think packed beds, we like to assume that it's plug flow, and then there's axial dispersion models. There's this whole family of models that we can use to approximate the flow of the deviation from plug flow. So this simulation definitely showed that there's a higher velocity at the wall. This is temperature, but we know that the profile of temperature right here is mostly caused by the velocity, higher velocity at the wall, and the slower moving fluid having to move its way through the complex structure inside of this packed bed. If we take a closer look at the mass fraction of each one of these reactants, so H2CO2 are the reactants and the products CH4 and H2O, we can see some interesting behavior. First, we see H2 comes in at a high mass fraction. And then we see, of course, because flow wants to push around these solids, we still see this high mass fraction of H2 that's leaving the system. We see in the slower moving fluid, we see that it's being consumed inside the core of these packed particles themselves. One thing you might notice, and that's very similar throughout, one thing you might notice is that there's reverse flow at the outlet. So that's why you would see this sudden change and return to the entrance values, or everything was zeroed. So this could be gotten rid of by extending this packed bed up to an empty tube by maybe 0.5 meters. For this case, I really didn't want to do that because the mesh was already large enough and I wanted to take a look at the results. So I was very anxious to take a look. So there's reaction and dispersion. We can see that this consumption spreads out. We see this cone right here of hydrogen. We can see this cone right here of product formation. And so we see some very interesting phenomena that's happening inside of this. One really interesting thing that I noticed just right when I made these cuts was that you'll see that there's a drop in consumption, or a drop in mass fraction of these particles, even though the mass fraction around the particles is actually higher. So we'll see this sudden drop of the local mass fraction of, say, H2, and then it drops down to 0. So what does this actually mean? Well, it means that there's a thin shell of reaction, and we're actually seeing these diffusion limitations. So that complex structure of the tortuosity and the porosity combination has reflected, has produced these diffusion limitations in this reaction. Now you'll notice the particle right next to it, it has a fairly constant concentration of H2 throughout the entire particle. And this is interesting because when I ran this case, I specifically selected out this particle and specifically lowered the tortuosity of that particle to see the effect, to see if this was just an anomaly, or to see if this would agree with a phenomenological perspective of, if I removed that diffusion limitation, what would happen. And in reality, what happened was the lowered tortuosity removed these diffusion limitations. So it's actually a very interesting result that agreed more with kind of an intuition that one might have looking at this. Okay, so let me leave you with some take-home messages. First of all, multi-physics simulation is a grand challenge that needs to be met. It needs to be met for so many different reasons, to solve lots of challenges that humankind needs to conquer. And there's lots of great researchers in the OpenFOAM community that are working towards this. And within ENGYS, we've developed this unified solver framework to enable multi-physics in a very efficient manner, efficient in terms of it reduces duplicate code, it reduces end user interaction complexity, and it creates a maintainable framework for developers to build upon, and it modularizes these interconnected solvers. Overall, the success of this application of heterogeneous Catalysis, in my previous life as a graduate student, these results could have taken me years. I'm not even exaggerating. And the success of this was completely dependent on, well, it was dependent on more than just having a solver. It was a meshing solution. It was being able to quickly set up. It was the solver itself. It was post-processing. It was support. It was being able to ask a developer who had written something else or ask the meshing developer who wrote an algorithm in meshing. That was kind of the key. And overall, one of the successes is an overall reduction on data management complexity. So we have these really complex workflows of scripts and things like that, but things can be very much simplified by using something like a unified solver framework. And that was really part of the whole solution, was this more than just a solver. And on that, I'll get some questions.
Okay, thank you, Daniel. That was a very good presentation. So we got a few questions here in chat.
Okay.
So first one is, how do the coupled wall boundary conditions for heat look like compared to a non-porous solid/fluid interface, e.g. the transmission condition?
I would probably, if my colleague Eugene de Villiers is in the chat, I can let him answer that question. I personally didn't develop this. The developer was Oliver Oxtoby, and I can make note of that question and answer that more completely in either the chat associated with this presentation, if that works. But great question.
All right. Yep. And then another question. It seems to me you are close to DES resolution with the mesh, but I believe you are running a RANS turbulence model. Wouldn't it be better to switch to DES since there is virtually no cost involved?
Yeah, it totally would. And I would love to do that, but to be honest, the meshing resolution was really down to that level because I needed to be able to resolve a lot of like these small features and small contacts and things like that within the kind of the particle structure itself. I'd be willing to try that. And one of the reasons that I haven't really is because, well, then we're moving to transient. Even if we do a pseudo transient with the DES, it doesn't really gain me too much. In fact, it might hurt me. And DES, if we've got these, vortex shedding off of the particles are in such close proximity to each other. I don't know if I would really gain that much more information. And, even though a RANS might still be better for that. But that's a great question too.
All right. And then another question. The Helix mesher can be used directly in OpenFOAM as Snappy, or it should be used from the Helix software?
Yeah, so Snappy was the predecessor, and I say that very, two of the three developers that created Snappy HexMesh. And, I'd say since the 10-year period that we started at ENGYS, a lot has changed. Now, there are some familiar things within the dictionaries that drive Helix HexMesh, but in terms of the code, no, there's a lot of different things that have been added since then. In terms of the interface, there are some components within the Helix HexMesh dict that might match with the Snappy HexMesh dict, but overall, it needs to be run with Helix Core.
Yep. And we've got about 30 seconds left. Okay. So here's a question. Is the code for this framework available somewhere?
It is available, and we provide it as part of our support contract through Helix. And if people have any questions, they can visit our website to see how they can talk to us about purchasing that software. Thank you.